Okay, hey there again, Science and Cooking, and let's finish up problem number 5. So I'm going to try and go ahead and barrel through parts E, F, and G in one shot here, building on the things we learned in earlier uh, subsections of this problem. Okay, so for part E, we're asked to think about the difference between water loss and other processes that might happen during the cooking of a steak. Um, we're told that um, we're told to imagine that the decrease in mass from 70 grams to 51 grams from the raw steak to the cooked steak is entirely due to water loss. Um, and we're asked to calculate the percentage by which the steak has shrunk using the fact that the density of steak and water is about the same. So there's a lot of things being talked about here. Let's start with density. Um, if density is coming into play and we're thinking about how much something is being shrunk, we are actually talking about a physical, visible shrinking. You can see something shrinking. It's decreasing in size as we perceive it, just looking at it. This actually means the volume has shrunk. I can't actually see how much something weighs by looking at it in terms of mass. Weighing it on a scale would tell me that. But I can see how big something is. So thinking about density, what we can actually do is convert the masses we've been given, the 70 grams and 51 grams of steak, to volumes of steak. We're told the density of steak and water is about the same. The density of water, which I'll write down as this funky Greek symbol, rho, that's a rho. Okay. The density of water is 1 gram per cubic centimeter. That tells us how much mass 1 gram is occupied by a given volume. In this case, a cubic centimeter, a tiny little cube, 1 centimeter on the side of water. We're told that steak is the same thing. So that basically means we can take this unit conversion. This is a unit. 1 gram of water and 1 cubic centimeter of water are the same thing. So this would be a 1. Something divided by itself is 1. And we can calculate volumes so for example, the raw steak, if it's 70 grams, we can multiply it by this unit conversion. Nice thing about unit conversions, they can always be turned upside down, and it's still legal. Because, again, they're equal to 1, so flipping it over is not going to change that. It's still something divided by itself. And we can realize that the grams will cancel, and our 70 grams of steak is also 70 cubic centimeters of steak. Now we can answer the question, by how much has the steak shrunk as we would visibly perceive it? Well, the new volume of steak, which would be similarly calculated, is 51 cubic centimeters. The old volume before it was cooked was that. Canceling out and working out the calculator to do this calculation, I see that this is 0.73 or 73%. 73%. Sorry. Okay, which is sort of there, but not quite there yet. The answer to this question is actually by how much has it shrunk. So if the new thing is 73% of the old thing, then it is actually shrunk by 100% minus 73%, which is 27%. And that's how we get the answer to that. Okay, so if something is now 73% of its former value, we can also say it's shrunk by the difference between that and 100%, which is 27%. Okay, so moving on to the next part, 5F. This is kind of a hypothetical here. We're asked to imagine that the change in elasticity from the raw steak to the cooked steak were entirely due to water loss. Then what would the elastic modulus be of this new stake, which has only lost water? Nothing else has happened. So we're kind of taking away the effects of heat here, which would denature those proteins and cause those cross-links to become closer together. Um, so thinking about this change in volume and thinking about length scales, okay, length scales, because that's what volume is. It's something that's defined in terms of length. Cubic centimeters is a centimeter times a centimeter times a centimeter. Okay, if we know the new stake volume is some length measure smaller than the old stake volume, the raw stake, we can use that information to help us calculate the hypothetical elasticity due to water loss. Um, so the easiest way to do this problem is to kind of think about our equations that are available to us. There's no pressure, there's no stress over strain here, so we're not going to be using that first equation. Let's think about the second equation and what it could do for us. Second equation is that. And we have a Boltzmann constant and a temperature, okay? Those will probably just be assumed to be, room temperature, and we know the Boltzmann constant. But we have this cross-linking distance on the bottom, and that's where this all kind of comes together with this problem. We know that the cross-links became smaller, okay, because this thing has shrunk in size. So these cross-links are actually now closer together. The question is, how much closer? Well, I know how much the volume shrunk, but that's different than saying how much the length of one side shrunk. So thinking about three-dimensional shrinking versus one-dimensional shrinking, those are different things. However, there's a kind of nice way around in this problem to not even have to worry about that and to just realize that I really want to know how much the cross-linking distance cubed has shrunk, because that is what's going to help me calculate the new elasticity after this water loss has happened. So how much has that cross-linking distance cubed shrunk? Well, a length cubed is actually a volume. So if I think about cross-linking distance kind of being part of a cube, hypothetical very small cube with the cross-linking distance L on each side, the volume of that cube would be L cubed. So if our big old chunk of steak has shrunk by 27%, our hypothetical tiny little cross-linking cube is also shrunk by 27%. And we can say that the new cross-linking distance cubed, which is our cross-linking volume, we can think of it, shrunk by 27% is now 73% of the old cross-linking distance cubed. Therefore, our new cross-linking distance is part of the new elasticity, and the old cross-linking distance part of the old elasticity. Okay, so I'm really interested in this new one here, so I'm just going to start writing that. But I don't know the new cross-linking distance. However, I do know the old one. I have calculated that already. That was calculated way back there in part C. So I can plug in, okay, I don't know that new one, but I know the old one. And moreover, I'm going to argue here, we actually don't even need to plug it in. We can actually use this. The new is equal to 0.73 of the old cubed. Okay. Why don't we need to actually plug any numbers in? Well, notice that the old elasticity is now given by this expression here. Those two things are the same thing. That means we can just substitute one in for the other. This is kind of doing a bunch of things at once here, although I think thinking about it graphically like this is helpful. So this big mess of variables, kBt over L old cubed, is the old elasticity. So I can just simply go ahead and plug that right in for that.